All right, 3.5, Introduction to Functions. So, we've been talking a whole bunch about equations, right? Equations and some inequalities like we did last time. But now we're going to talk about functions, and functions are essentially equations that are more special. They're basically functions are basically equations that have special properties to them. And we're going to start back at the basics. So objective number 1, we're going to talk about independent versus dependent variables. And I know that sounds super scary, but they're just x and y. It's the x and y you've used this entire time. So let's consider some situations, some real life situations, because that's where you would see a function, and that's where you would start defining the variables to match, right? Alright, so consider the following situations. The amount of your paycheck if you get paid hourly for a certain number of hours you work, right? So there's two things we're talking about here. The amount you get paid and how many hours you work. Now one of these is going to be considered the independent variable, the thing that doesn't depend on the other one, right? And then obviously the dependent variable depends on the other one. So let's consider what's dependent here, right? Is the amount you get paid dependent on how much you work, or is how much you work depending on how much you get paid, right? So it's kind of like, which one can stand alone? That would be our independent. Well, you can work as many hours as you want, right? It doesn't matter, well, within reason, right? There's always that overtime and all that jazz discussion, but really the hours are the independent thing here, right? You work no matter what. You work 6 hours, you work 8 hours, right? It doesn't matter how much you get paid for how much you work, right? People still work all the same hours. If Joe is making $6 an hour and he works 5 hours, and Billy's making $12 an hour, but he also works 5 hours, they both work 5 hours. Notice it's not dependent on that, right? So this is what we call our independent variable, and our independent variable is always going to be x. So a certain number of hours you work, that's going to be our x. X is always the independent variable. Now, since that's independent, right, we can even make that note, independent, put it in parentheses, then something's got to be dependent, right? So what would be dependent in this situation? If x is you work so many hours regardless of your paycheck, well then your dependent thing has to be the amount you get paid, right? That's got to be how much you get paid. That depends on how many hours you work, right? So that would be our dependent variable. That would be y. Dependent. Dependent's always y. So y depends on x. That's always a true statement. Let's see if we can do the same thing for the couple other situations. So the cost of gas, depending on how much gasoline you put in your car. That one's kind of a little more straightforward, right? They even told us, depending on how much you put in your car. The cost of gas depends on how much you work in your car. So this again, this cost of gas is going to be our dependent, our y, while the gasoline we put in our car, how much, is going to be our x, our independent. You can put as much gas as you want in your car. It's not going to change, how much, the cost of the gas is not going to change how much you put in your car, right? I still have a 10-gallon tank. I need to fill that 10-gallon tank no matter how much they're charging me for it, right? Now, again, we could argue that maybe you don't have enough money, and that's where it gets a little bit of a debate, but still, here it's definitely, it's not going to matter how much the gas is when you're putting it in your car. What will matter is how much you have to pay for it, right? The ending cost is going to depend on how much you put in your car. And then finally, we can think about the distance traveled by a car moving at a constant speed for a certain amount of time. So what would be the independent variable? I encourage you to pause the video right now and talk about it as a class, and then we'll discuss it in just a sec. Alrighty, I hope you had a chance to stop and talk about it. Here, the independent variable would be that constant speed, that speed for time, right? So, I'm sorry, wouldn't be the speed. The constant would not be the speed. Oops, how much gas you put in. The constant would be the time. The time would be the independent variable. It would be independent. The speed would actually be the rate. We're thinking of that equation d equals rt here. And so r would be our m, our slope, right? Our speed would be our slope. But the time would be the independent variable. So you could even label it t if you wanted to. But here, time would be our x. Time would be our x. And then what would be our y? Our y would have to be something that's dependent on it, or in other words, the distance, right? The longer you go, the farther you will travel. It's not the farther you will travel, the longer you will go, right? That doesn't make any sense. But the longer you drive, the farther you will go. So this is sort of the relationship between x and y. X is always usually time or how much you're putting in the gas station, how much you're adding, things like that. And then y is the result you get out of that. So that's why we kind of have this independent-dependent relationship here. All right, cool. So let's look at another example where you have some more specific x's and y's. If you get paid $5 an hour, the table below, and again, mine's a little off, so yours should hopefully will be on the same page. I'm pretty sure it's on the same page. The table below represents your paycheck. X here is the independent variable, and y is the dependent variable. So what here would be, if we get a little more specific to the problem, what would be our independent variable? What would we call x? That's right, we would call x hours worked, right? So x would be this side of the table. X would be how many hours we worked. We kind of talked about this in the first situation. Whereas our paycheck would be how much we're actually making. It depends. If I only work 2 hours, I'm going to get paid $10. If I only work 6 hours, I'm going to get paid $30, right? So it depends on how many hours I work, and that's usually how we set up the table. So you wouldn't set up the table the other way around where X would be your paycheck, because that wouldn't make much sense. Alrighty. Now let's talk about relations versus functions. So like I said before, a function is a very special type of equation. Not a lot of things are actually functions. Most of our linear equations are functions, and we'll get into that in just a sec. But a function is a very special thing. It's actually a very special type of relation. So let's talk about relations first. Relation is a set of ordered pairs. That's what it comes down to. It's relating to things. So everything we've talked about today already is a relation. 2 to 10. 4 to 20, 6 to 30. There's your relation. It's a set of ordered pairs. So it's any two things that are related. Yeah, that's pretty much it. Anything can be a relation, but if you want to be a function, it's required a little bit more. A relation is just a set of ordered pairs, but a function actually has this thing called one-to-one. One-to-one. And that means that for every independent variable, let's see, we can even read it. For each independent variable, there is only one dependent variable. So that means for each x, there is only one y. For each x, there is only one y. So you cannot, if I had this list up here, we go back to this list we were talking about, notice that when I work 2 hours, I'm only going to be paid $10. There's no other choice, right? There isn't some step ladder bonus system or whatever. It's just you work 2 hours, you get paid $10. Same thing goes for 4 hours, you get paid $20. Same thing goes for 6 hours, you get paid $30. Like, that's it. There is no other option. So if a relation has one x and it's going to 2 different y's, meaning if maybe I work 2 hours and I had a choice between getting paid my hourly wage for $10, or if I take a commission of $15, that's not a function. Since I have a choice there for that 2 hours, that is not a function. Alright, so let's take a look at some more ordered pairs. So these are definitely relations, right? These are all ordered pairs, F, G, H here. And we're going to decide if they're actually functions. Now we can call them F, G, and H all we want. F isn't specifically designed for a function. It's used quite often, though we'll talk about that a little later. But let's take a look at these ordered pairs. So here I have F. For each of the x's, I'm going to underline it in blue. I have 1, -2, and 3. So let's take a look. In this first ordered pair, 1 goes to 2. That's what we're looking at. 1 goes to 2. So for the x of 1, let's make a little table over here for F. For x of 1, then y is 2. That is the only thing I see, right? So that's what that ordered pair tells me. For x is 1, y is 2. Excuse me. What does it say for the next pair? Well, it says that for x of -2, y is 4. That's what it says, basically an ordered pair, right? And then the last one, for x equal to 3, y is equal to what? That's right, -1. So basically I'm just splitting up those ordered pairs, right? Now what I'm looking for is, in order for this to be a function, remember, a function says that for every x, there's only one y. There's only one specific y. So do we see any x's being repeated? Do we see 1, the number 1 going to 2 and 4? Do we see 1, 6, 1, 9? Do we see any of that? No, it doesn't look like that. We have 1 to 1 here. So this is 1, 1, and 1. So we've got one x going only one place. So this is indeed a function. We can put a little check mark for function. Let's do the same thing with g. If you want to make the table, you're more than welcome to. I'm going to do it, but some people can just kind of pull it out looking at the pairs. If you see any double x's, you can do that. Totally fine. But I'm going to make another table over here for g. I'm going to have to write a little smaller because it's a little bit bigger, g. But again, we've got our x's and our y's. Okay, so the first point here, it says that when x is -2, y is -1. So I'll write -2 and -1. Here I have -1 going to 0. My next point says I have 0 going to 1, and I'm very, very careful about where I'm placing these, right? The x's always go in the x column, the y's always go in the y column, right? So I have to make sure. All right, now I have 1 going to 2, and lastly I have 2 going to 2. All right, so let's pause right there, because I've already written a 2 down. So what I'm going to do is I'm going to say that 1 goes to 2 and 2 goes to 2. So I'm going to kind of draw this little thing in there to tell myself these are both going the same place, and that's okay. Some people just like to make what we call a mapping. We'll talk about that in just a sec, but I prefer the table chart. So as long as you don't double up. That's the thing you want to remember. Don't double up. Don't write values twice. Okay. Now let's look at this. We have to be very careful because this last one's a little bit tricky looking. Up until then, it seems we've got pretty 1 to 1, right? -2 is only going one place, -1 only is going one place, and 0 is only going one place, right? But then we get down to this situation. We have to be very careful about the wording. Let's be very careful here. It says for a function, each x only has one y. Does it say anything about the x's sharing a y? It doesn't, right? So it's okay that they share a y. So let's take a look here. 1 only goes one place. If I asked you what is paired up with 1, you would say 2, and we would all say 2, and we would all be right, right? There would be no other person who said 3 and was also correct, right? It's just 1 goes to 2. Same thing with 2, right? 2 only goes to one destination. 2 goes to 2. That's it. That's the answer. If I were to ask you, what is the y when x is 2, everyone here could give me the correct answer of 2, right? That's it. There wouldn't be any other answer. So this is actually a function. This is a function. Even though they share a 2, that's okay. We just can't have we just can't have an x having 2 answers, right? We can have a y being the same answer, but we just can't have an x having 2 answers. Excuse me. Alrighty, let's take a look at h now. Let's take a look at that h. Let's do it in green. Alright, so h we'll put down here. Do the same exact thing. Same exact thing. So we've got -4 goes to 1. Set up our little table. Alright, so -4 goes to 1. -2 goes to 0. And -2 goes to 1. And again, I don't want to double up, so I'm not going to write -2 twice, right? I'm not going to write it I'm not going to write it for every time I see it. If I see it once, I'm just going to write it down. Now, if there was a y that was a -2, of course, I'd go put that in the other column. By doubling up, I mean don't double up in your column, right? It's okay. Like here, back in G, I knew there were 2 zeros, but one of them was a y and one of them was an x. Here, since 2 x's are -2, I only write it once. All right. Let's decide. Is it 1 to 1? Well, this first one, definitely, right? -4 is only going one place. But then we hit down here. -2 goes to 0. And -2 also goes to 1. So if I were to ask the question, where does a -2 go? Or in other words, what is y when x is -2? Well, we have a problem. Half of you could say 0, and half of you could say 1. And you would both be right. You see how that happened? So this is not a function. This means that there are 2 y's, 2 dependent variables for one x. For -2, you have 2 choices. So here's 2 choices. Let me erase that. 2 choices. And that's not a good thing. You don't want choices in functions. Think of it this way. If you told a computer to spit out the answer to -2 and it had 2 choices, the computer would break down. That's why we want to do, that's why these functions are so important. So we can't have multiple choices. That's the reason we don't want them. So this is not a function. Not a function. All right. If you have any questions at all, please pause now, and then we'll return in just a sec. Alrighty. The third thing we're going to talk about today is domain and range. You may have heard these terms before. You may remember hating them, but honestly, they're really not that complicated. Domain is all of your independent variables, all of your x's. So domain, we'll even use a different color. Domain is your x's, or think independence. Your range is going to be your y's. Think your dependence. Now, the only problem with this is when I say think of your x's, I mean every possible x value. So here in the functions, there are only, or here in the relations up here, there were only a few x values, right? And that's okay. Sometimes, though, with equations, they get a little bigger. But let's practice with domain and range here in this example first, and then we're going to decide if this is a function or not. So let's list our domain. We'll call it D. Let's put it in the same color. D for domain. Okay. And then we're going to write a curly bracket. And we're going to do a lot better job than that. Curly bracket. There we go. And we're just going to list all of the x's we see in this relation. So let's start with 3, 4. Let's see. There's that one. That one. I've already written 4. So again, I don't have to write it twice, right? It's the same thing as our tables in the last problem. And 6. There's my domain. 3, 4, and 6. Those are the only x's I see. The only possible x's. We're done. Let's do the same thing for range. Range is all of our possible y's. Well, I see a -1, a 2, a 5, and an 8. Alright, there's my range. Didn't have to double, there weren't any doubles, so I didn't have to worry about that. And those are my domain and my ranges. This one is very, very specific. For specific ranges, for specific domains and range, you use a curly bracket. Okay? We'll talk about when we don't have a very specific one later on, but right now, you just use a curly bracket, you list what you see. Let's decide if this is a function. What do you guys think? Do you think it's a function? Do you think with this domain and range, do you think it's a function? Alright, I hope you said that it's not, right? Because we have 4 going to 2 different places, and 4 is in the domain. 4 gives us 2 answers, here to here. 4 could be 2, and 4 could be 5, right? That's an issue. We can't have 4 being 2 things. Now, if 4 was on the other side, if 4 was in the range, and that would be okay, right? It's okay to have the 2 of the same answer, just not okay to have 2 different answers. Alrighty, so we would say that this is not a function. Alrighty, let's move on to B now. It looks like C kind of got dropped down. So this is what we call a mapping. Sometimes you'll see it this way. This is called a mapping, where it's very similar to our tables. They just take all the x values, put them on one side, take all the y values, put them on the other. Or take all the independent variables, put them in one bubble, take all the dependent variables, put them in another bubble. It's just a little organizational scheme. It's essentially what we were doing up here, but since, I don't know, I'm a table person. If you want to use the circles, go for it. I don't really care. What do we think here? So domain, let's start with domain. What domain do we have here? It's a very specific domain. Well, it looks like we could go, let's try and go in order, because just for simplicity's sake. You don't need to go in order in curly brackets. Technically, that's not a rule, but eventually you will need to go in order for numerical order for intervals. So let's just practice that now. Looks like we have a 76 and an 88 and an 89 and a 95. And that is all of our domain values. Then we've got our y, our range, right? Our range, whoops, pink, is going to be all of the y values. And the y values are A, B, C. You'll see that type more with like coding and computer stuff. If you want to return like a phrase, right? And the person needs, there's stuff like that. So if you're into coding, you've probably seen that before, where your range is more of an A, B, C kind of thing. You can return stuff. A lot of numbers involved too, but this is something you'd see more in coding. All right, cool. Now let's decide, is it a function? Well, let's be careful. I see something that is going to the same place, but is that okay? Talk about it for a sec. Is that okay, or does this mean it's not a function? Alright, I hope you paused the video and actually talked about it, but this is definitely a function. Yes, notice there's only one answer. 89 goes to B. That's it. It doesn't go two places, right? It's not 4 to 2 and 5. 88 only goes to one place, to B. If I plug in 88, there's only one answer. Therefore, this is a function. Yes, function. One input, one output. One input, one output. They happen to be the same output, that's okay. But there's one input, one output, right? It's not two different numbers. Alright, let's do this one. C. Alright, what's our domain here? The domain's going to be, that's right, all of our x's. All of our x's. Our x's are -5, 0, and 5. So we'll put it in curly bracket. -5, 0, and 5. Curly bracket. And then our range would be all of our y values. Now remember, just like in our tables, we don't want to double up. So what they've given us here is a range of 2. That's it. Don't ever copy or don't have multiple copies in your domain of ranges, right? -5 and 5 are two very different numbers, but 2 is the same number. So what do we think? Domain, or do we think function or not a function? It's actually a function, right? Each one of these x's is independent. It has only one answer. -5, the answer is 2. 0, the answer is 2. 5, the answer is 2. Yes, they all have the same answer, but that's okay. It's one answer. Yes, it is a function. It's a function, right? It's a very boring function, I will tell you that. And basically return value of 2. That's awesome. Who cares? It's just 2, right? But sometimes those are important. So yes, this is a function. Now let's take a look at these guys. So graphing. Before we do though, I really encourage you to stop right now and ask any questions you may have about domain and range for these kind of functions. We're going to go on to graphing and talk about a certain test we'll use. Actually, you know what? Yeah, we're going to do that. So pause the video now if you have any questions at all, and then we will start talking about the graphs. Alrighty. So when it comes to a function on a graph, you have two options. You can pull out a few points, like here. On this graph here, we only have 4 points. So it might be in our best interest to actually write these 4 points down and then do the problem like we did in example A. So let's start with that. We're actually going to start with this second graph here. Let's see, I have the points. Let's take a look. This first one over here, the leftmost point, is back 1, up 1. So -1, 1. I know, I'm so sorry that the graph is a little off. These should be 5s, not 4s. So my apologies. These should be 5s. I don't know what happened with my labeling. It got a little off. So if you'll notice, there are in fact 5 spaces in between that. So this would be -5 and this would be a -5. Alright, so that makes this first point here, this red point, -1, 1. Then we'll go to this pink point down here on the y-axis, which means out 0, right, and down 1 gives us a 0, -1. Over here, we'll call it a green point up here in the quadrant 1. Remember way back when, quadrant 1? That would be out 2 and up 3-ish. Out 2 and up 3, right? And then last, and I'm just rounding here to the nearest whole number, would be out 5 and down 4. So I'll do 3, I'm sorry. Out 5 and down 4. Alright, so those are our 4 points we see on here. And let's see if we can do this in our head. What would our domain be? Our domain would be -1, 0, 2, and 5, right? -1, 0, 2, and 5. Pretty straightforward. Our range, 1, -1, 3, and 4, right? All of the x values and all of the y values. And just from looking at these points, what do you think? Function or not a function? That's right, it's a function, right? We don't see any repeated x's. If we saw a repeated x, then we would have a problem. There would be one x going to 2 different places, 2 different y's, and that would be an issue. So this is a function. Yes, a function. We'll just write yes. Awesome, so that one's pretty straightforward when it's just points, right? When it's a nice, easy relation and you have only a few things, and that's the stuff we've been dealing with so far. But what about something like this? This has a lot of different points. Not only does it have these points that actually hit like markers, right? It has one like right here, but it's got all of the points in between. And even if there were arrows on the end of this, it would have infinite number of points, and that would be an issue. So we wouldn't be able to look at every single case. We would be doing it forever, and nobody has time for that. Ain't nobody got time for that. So instead, what we can think about is, I meant to erase. What instead we can think about is whether we see anywhere on the graph that hits a certain x twice. So let's take a look real closely. If I were to draw a vertical line, right, because that would be the line x equals something. Right here it would be the line x equals 4. So this blue line is x equals 4. It only hits at how many points? How many points does this yellow line hit the blue line? Good, it only hits once, right? And if we assume the pattern continues as such, it's only ever going to hit at one point, right? That one point. Let's draw a different line. Let's draw the line x equals -1. So this x equals -1 here, this vertical line. If x equals -1, this vertical line, then how many points does it hit at? Again, it only hits at 1. Good, it only hits right here. It's never going to zoom back and we assume, right, that it's not going to turn back and hit again. So this is what we call the vertical line test. If you look a little farther down the next objective, it's got it right there for you, the vertical line test. We take a vertical line through all of these and we basically run it across the graph and we see, is this x ever going to hit twice? And remember, if it hits twice, that means you have the same x going to two different places, right? So if it doesn't hit twice, then it is a function. This is a function, yes. Let's take a look at an example where the vertical line test fails, where this doesn't work, right? So let's go take a look at the first one. This is a nice pretty oval, right, or an ellipse if you're a little more technical about it. Let's draw a vertical line here. Let's draw the vertical line through 0, right? So this is x equals 0, otherwise known as the y-axis. X equals 0. So this nice pink line. How many times does this one hit? I know it's not really represented in my little box, but look on the whole page. How many times does this one hit? That's right, it hits twice. Once up here at the top, and once down here at the bottom. And if we think about it, that means we have both points. We have the point 0, 6, and we have the point 0, -6, which is a problem. We have one x, 0, going two different places, 6 and -6, and that's an issue, right? That's not a function. This fails the vertical line test, so this is not a function. Not a function. Whoops. This is not a function. So notice that when you draw that vertical line, you are testing to see whether you have one of these kind of cases, whether you have a -2 going to two different places. It's not always going to be a circle, but sometimes some functions or some relations will fail the vertical line test, and therefore they are not functions. Let's do a few more examples. So it looks like I've just doubled up on that, so let's do a different example. I'm going to draw a graph for you guys down here. These ones we just did, so maybe we can do the domain and range, but we're going to decide whether these are functions. So I'm going to draw you a different graph. You guys tell me whether you think it's a function or not. So just for your information, this is the line y squared equals x. I know that seems a little backwards, but it's true. This is the line y squared equals x. What do you think? Function or not a function? All right, talk about it. Pause the video and talk about it. All right, I hope you said it's not a function, because clearly if we were to draw a vertical line here, it hits twice. Any vertical line, we don't even need to know where that vertical line is. It happens so many times that this is definitely not a function. So this would be a big fat no. No, not a function. All right, cool. If you have any questions at all, make sure you get them answered, pause the video. But we're going to talk about domain and range for these guys now, since we kind of missed that earlier. Domain and range we talked about with this one, right? We talked about the domain and range up here. For here, we've deduced that this is a function. Yes, it is a function, right? So we figured out that, yes, this is a function. But what's the domain here? And we're assuming it goes on forever. So we're assuming there's little arrows here. The domain would be what? Well, it would be all of our x values, right? And those aren't specific here, right? We talked about that. That's the fact. There are too many to even question whether it's a function through this sort of, check method. We had to use the vertical line test. So because there's too many x's, we have an infinite domain, right? So we have what we have here is anywhere along this line, it's going to hit an x. Here we find that x. There we see another x, there's another x, and another one, and another one. It's going to keep touching every single x value for as far as we can. So how we would write that is we're going to say it's from negative infinity to positive infinity. And yes, those are infinity signs, not double zeros. Here we go. From negative infinity to positive infinity. So all these x's over here will eventually touch. Yes, they're not on the graph, but eventually they will be used to all of these x's over here on the right. Those will all be used as well. So it's negative infinity to positive infinity. Notice I did not use curly brackets because this is what we call an interval. It's from something to something. So I'm not saying just negative infinity. Excuse me. I'm not saying just negative infinity to infinity. I'm saying everything in between. So everything from negative infinity all the way up to negative 1, 0, 1, 2, 3, 4, 5, all the way out to infinity, right? So that's an interval. It's not just curly brackets like we've been using before. These aren't very specific. These are general. All right, cool. Let's do the same thing with range. Range, I don't want to use pink. I'm over pink. Let's use green. Range is the same thing. We're going to look at the y values. Is there any y value it's not going to touch? Well, that touches that one right there. It touches that one right there. Touches that one. And by touches, I mean if I were to graph this point, if I were to, pick a point here and write down this value, that would be 0, 6, right? So eventually it hits 6, eventually it hits 8, eventually it hits negative 5. So it looks like this one too also goes on forever. It's going to touch all of those y values, every single thing. So again, this one is also negative infinity to positive infinity. My infinities kind of suck, so that's fine. Alrighty. Now let's look at, so hopefully you got that. Make sure you pause the video and get questions answered. But let's take a look at this domain and range. No, actually, let's do a different one. We're going to pick something like this. So over here on the side, draw yourself this function. And I've already told you it is a function because it only hits x's once. It doesn't double back. It looks like it passes the vertical line test. This is actually an exponential equation. We're not really going to touch on those much this year, but let's take a look at the domain and range here. So the domain is going to touch oops. What did I do? Yeah, it's going to touch every single x, right? It's going to touch every single x, meaning that at some point I'm going to have x equals negative 5, x equals negative 7, x equals negative a million, x equals a million, positive a million, right? Eventually it's going to touch every single x. I'm always going to have a point like that. So the domain is still going to be negative infinity to positive infinity. But now let's be very careful about that range. What range values does it seem to take? Well, it's got these positive ones, right? It's got these positive ones. And it's got these positive ones. It's getting a little hard to tell, but it seems like it's going on. Does it ever look like it's going to go into the negatives, though? No, it doesn't. It's not going to go down here. That's not any range value. So we're not going to have anything below 0. Sometimes that happens. How we would write this, what am I doing? The range would also be an interval. And we've already deduced that it's going to go up to infinity, right? It's going to get all the positive values. But what is it going to start at? If it's never going to go in the negative, where is it going to start? What do you think? And I hope you said it's going to start at 0 because that is correct. It's going to start at 0, right? So it's going to start here at the 0 line and then go up to infinity, right? That's where all the range values are going to be. We already talked about domain. It's going to hit all the x's, right? The x's are represented by the red, but the range values are going to start at 0. It's not going to go into that negative zone. It's actually just going to go from 0 all the way to the top. All right, cool. All right, if you have any questions about finding a domain and range from a graph, make sure you pause the video now. I know I'm saying this a lot, but domain and range is an area where people have a lot of trouble. So I want to make sure you guys are getting this as you go along, right? It always gets more complicated as we go. So please make sure if you're stuck now, get those questions answered so you're not sitting there frustrated the entire time. Alrighty, let's look at identifying domain and range from an equation. So from an equation, let's do domain and range, and then we'll do function too. We'll have to tell if it's a function from the equation. Alrighty. So y equals x plus 4. Let's look at this carefully. Y equals x plus 4. Well, is there anything xy? Well, let's start with the domain and range. Domain. Start with that domain. What domains am I allowed to put in here? In other words, what numbers what real numbers am I allowed to put in for x? X is that independent variable, and it seems like x doesn't have any problems. What numbers am I allowed to put in there? That's right, I'm allowed to put anything in there, right? Anything can be added to 4, right? Any number. 2 can be added to 4, 1 can be added to 4, 500 can be added to 4, pi can be added to 4, right? So this is actually an infinite domain in both directions. I can put any number I want to and add 4, right? And when I do that, I can get any number back, right? I can always solve this equation for any number. I can plug in any range I want to and solve this equation. So I can also, here I also have an infinite range. And if you don't believe me, I dare you to try it. Find something that you can't plug in a value and find the other one. That's really what we're asking here. Is there anything you can't have in your domain and range? If the answer is no, then you can write down you have an infinite domain and range. Alrighty. So what does that mean? Does that mean this is a function? Absolutely it means this is a function. It means that for every... Well, it doesn't mean it's a function, I apologize. There are relations that have infinite domains and ranges that are not functions. But we've already discussed something that looks like this. If we looked on the graph, right, this would be the line starts at 4 and goes up 1 over 1. And we've already deduced that these linears are functions, right, because they pass the vertical line test. So, yes, this is a function. Alright, let's take a look at the next one. Y squared is equal to x. Well, we kind of already discussed whether this one was a function or not, right? We looked at the graph way back when. That's what it kind of looks like. But let's talk about y. Why would this not be a function? Let's look at that domain and range. Domain and range. Come on. There we go. Domain and range. Well, let's take a look at what I'm not allowed to put in there. Let's rearrange it a little bit. If I take the square root of both sides, then y is equal to the square root of x, right? So y is equal to the square root of x. All I've done is square root both sides. What cannot be under a square root? Dig way back when, think about that. What cannot be under a square root that wouldn't give you a real number that you could graph? That's right, you can't have any negatives, right? This is a, well actually, no, scratch everything I just said, because those are not the same function. Okay, sorry. Let's think about the domain and range the way we've been thinking about it. So, are there any x's that would give me the same answer, right? So let's take a look at y is equal to 4 and y is equal to negative 4. So here's a situation that would give me the same x. So here, let's see, what's 4 squared? So I'm plugging it into the equation. Y equals 4, so if y equals 4, then 4 squared equals x. So here x is equal to 16. So x is equal to 16. So here technically I have the point 16 comma 4, right? X comma y. Let's look at this other case now, the negative 4. What happens when I plug that in? Well, I would plug in negative 4 squared equals, what does that equal? That also equals 16, right? So x equals 16. Or in other words, I have the point 16 comma negative 4. And now we can see, now that we have 2 points, that we have one x going to 2 different y's, 4 and negative 4. So we have 2 y's that give us 1 x. Or we have 1 x to give us 2 y's, and therefore not a function, right? Not a function. That's a problem. That's a problem. However, this domain and range is also infinite. This domain and range, we can still plug in anything. You can square anything you want to, right? And you can square root almost anything you want to. Oh, nope, I'm just kidding. Let's talk about the range. The range is infinite. The range is going to be negative infinity, positive infinity. You can square anything you want, and you can get anything you want squared. But the domain has to be what? That's where that square root part comes in. The domain has to be positive. The domain has to be positive. So from 0 to infinity. Otherwise, you're saying that negative 1 is something squared, and you'd be laughed at because you'd be wrong. We'll get into complex numbers later, but basically you're saying if I said x is equal to negative 1, then x is equal to y squared, or negative 1 is equal to y squared, and you'd be like, what are you talking about, you silly person? You can't square something and get a negative number, right? So the domain is going to be 0 to infinity, but the range, you can square anything you want and you can get a real number. Alrighty. If you have any questions, please pause here. I know I made a mistake or two. Hopefully you caught that. Discuss that amongst yourselves, and then we'll move on to C. Alrighty, inequalities. Inequalities are a little tricky when it comes to domain and range because we have so much more to think about. Remember how the graphs differ, right? A regular equality, an equation, is only going to have a single line, while an inequality is going to be an entire shaded side of the graph. So chances are these guys are going to have a little bit bigger domain and ranges. In fact, most of them are infinite. In fact, all of them are infinite, if I remember correctly, unless you have something strange. Anyways, and the ones I will be giving you, basically, they're all infinite. Let's take a look at why. So here, imagine this was a linear equation, first off. Y equals x minus 1, instead of y is less than or equal to x minus 1. The equal to part alone is a linear equation, and therefore we are back at the first example, right? Anything I want to, I can plug in there. I can subtract 1 from anything. Your 4 basic operations, I'm sorry, 3 of your 4 basic operations, addition, multiplication, and subtraction, have infinite domains. You can plug in any real number you want to, anything you want to. Division, what's the only thing you can't plug in? We'll talk about that in a sec. But here, since it's subtraction, it already has an infinite domain and range. On top of that, if we were to look at y is less than x minus 1, so I'm kind of breaking this into 2 pieces. You've got y is equal to x minus 1, that part. Now you've got the y is less than x minus 1. Again, there's going to be even more that's y could be, right? So if I plugged in x equals 1, I get 1 minus 1 is 0, and there's an infinite number of negative numbers that would be less than 0, right? And then same thing going around. There is same thing on the other side. I can plug in any x I want to. So this is, again, a domain of negative infinity to positive infinity. And so our entire range is going to be the combination of the two. I'm sorry, our entire domain is going to be the combination of the two, and so is our entire range, the combination of the two. Therefore, this inequality specifically, since it's so closely related to a linear, and the ones you will see in my class are so closely related to a linear, usually end up with domain ranges of negative infinity to positive infinity, meaning anything you want to, you could plug in there. Alright, one more. We've got y is equal to 5 over x minus 1. What is the issue here? Well, it comes back to what I was just saying before. 3 of your 4 basic operations, you can have infinite domains, right? Multiplication, addition, and subtraction, you can plug in anything you want to. What can't you plug into division? What can you not have when you divide? I really hope you said you cannot divide by 0. Don't divide by 0. Otherwise, your little brain will explode and so will your calculator. So don't divide by 0, which means there's an issue here. I can't end up with 5 divided by 0. So I have to be very careful. That doesn't mean x can't be 0, right? X can be 0. If I plug in 0 there, 0 minus 1 is negative 1. I get 5 over negative 1 or negative 5. There's an answer. Good, we're done. But here, I can't have this happen. So what I can't have y equal to 5 over 0. That can't do that, right? So what x value is going to make that happen? What's the only thing I actually can't have? That's right, I can't have x equal to 1. I can't have 1 minus 1 equals 0. So x cannot equal 1. If it equals 1, I run into a problem. I run into not a real number. That doesn't make, I can't run into this guy, right? And that's an issue. So how I would write this domain is I would say that x, so I would say, well, there's one of two options. You can use an interval. You can say x not equal to 1. You could say x such that x does not equal 1. Or you could say the domain, if we were using our interval, you could say everything from negative infinity up to 1, not inclusive, and the little u, 1 to infinity. Either one is up to you. If you want to say x such that x, you don't even have to use the x part. You could say x does not equal 1. You could write it in words, all real numbers not equal to 1. You could write this interval any way you want to express that. But you have to state some way that x does not equal 1. It cannot equal 1. That is not part of the domain. That's the important part of these guys. What can x not be? Now the range can be still anything, right? I can get anything out of that. I can solve that for y. I did solve that for y. I can solve that for x. And when I solve that for x, let's see, what's this guy to this? Well, you'd have to do some fancy things. But you can solve that for y, and it turns out that the range is still negative infinity to positive infinity. All right. So that's pretty much domain and range with equations. This is one of the hardest parts of the chapter, so I really hope you guys pause now and talk about anything we talked about and make sure you get all your questions answered before we move on to using function notation. Alrighty. Using function notation. Function notation looks like this. You've probably seen it before in your travels here at Alta High School. Basically, it's just a replacement of the dependent variable. So once you've decided that it is a function, you've decided that what you have is a function, you can actually say that by using this little symbol here, f of x. Please underline that. It's written somewhere. Maybe it's not written anywhere. You can write it on the side here. This is pronounced f of x. It is not f times x. It's definitely not x times x. I'll actually write the word not because that's less confusing. So it's not f times x. Please never, never, never say fx. Never, ever, ever say f times x. This is not Fox News. Don't call it fxx, right? It's f of x, f of x, and if it was like a g, it'd be g of x. If it was a s of t, if it looks something like this, that would be s of t. It's whatever's on the outside of whatever's on the inside, and we're going to make sure that you guys say it that way. The reason I'm so adamant about that is because when you say fx, you are inclined to actually multiply those two, and that is not possible. You cannot multiply them. That is not how this works, okay? So do not multiply them together ever, 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 ever. Okay, so it's not f times x, it's f of x. F of x. All right, I think I got my point across. Basically, once you decide that an equation is a function, all you have to do is replace the y value. So replace the y value with that f of x thing. Once you've done that, you can use it to evaluate. So once you've done that, you can do what they've done here. They said, okay, this equation, y equals 3x minus 4, is a function. And it is. We've decided that it is. It's a linear equation. It has an infinite domain and range. None of it overlaps, so it is a function. Therefore, it is now f of x is equal to 3x minus 4. The reason we'd want to do that, a couple benefits of this notation, is that you can show what you're trying to evaluate. So on here, they are trying to evaluate x equals 2. So in other words, they're plugging in x equals 2. So they plug it into every single time they see x. And this is important as to why we call it f of x. Because now on this right-hand side, or left-hand side, notice they never once multiply it by 2. It's not f times 2, right? It's f of 2, which means I am now taking this function and I am evaluating 2. I am plugging in 2. And that's what they do on the other side. And there they actually solve it down so you get a value, right? And so f of 2 equals 2. Let's try that out down here. Solve f of 2 and f of q for f of x equals negative x squared plus 3x minus 5. Or I'm sorry, plus 5x minus 3. So starting with this f of 2 thing, what am I supposed to do? What does that mean? What does this notation tell me I'm supposed to do with this function? Pause the video now and talk about it. Alrighty, I hope you guys said that f of 2 means we take 2 and we plug it in for every single time we see x, because that's absolutely correct. So here I've got 2 instances of x, right, and I'm going to make sure I plug this in. So I've got negative 2 squared plus 5 times 2 minus 3. And look how I did this first term here. It's very, very important. I put the negative on the outside. In the original function, that negative is not in parentheses, so the squared only applies to the x, and so the squared only applies to the 2. Okay, so watch out for that, because that's going to change this answer a little bit. All right, we'll simplify using PEMDAS. PEMDAS, right? Please, parentheses. Well, we don't have any really super valid parentheses here. We have one here, but that just means multiplication, and this one means exponents. So let's start with the exponents. We've got negative 4 plus 5 times 2 minus 3. Now we'll do some multiplication. Negative 4 plus 10 minus 3. And then addition and subtraction. And remember, addition and subtraction are interchangeable. It's whichever one comes first, right? It's whichever one comes first. So now we'll do negative 4 plus 10 is negative 6. Minus 3 is negative 9. So we've evaluated the function f of 2. Let's not do there because we want to save some room for that other part. So f of 2 equals negative 9, meaning when I plug in 2, I get negative 9, right? It's not f times 2. I'm not multiplying 2 to everything. It's I'm plugging in 2. 2 equals negative 9. Yeah, nope. Positive 6. I'm so sorry. No, it doesn't. They're all looking at me like I'm an idiot. Doesn't equal negative 9. It equals, that's a positive 6. Minus 3 would be a positive 3. Yeah, be a positive 3. Yeah, don't go so fast you make stupid mistakes like that, right? Even Miss K makes mistakes. Alrighty, so that's evaluating. Let's do the exact same thing for f of q now. You may be thinking, how the heck am I supposed to evaluate for f of q? Q is not a number. I have no idea how to times things by q. You're absolutely right. There is nothing we can really simplify down to a number, right? But this is just trying to show you a variable change. F of q is the same thing as f of 2. It's the same rule. Remember, variables are just numbers we don't know yet. So if I'm saying take this f of x and make it f of q, what are you supposed to do? Well, the same thing you're supposed to do with 2, right? Take all the x's, and instead of making them 2, make them q, right? So let's make all of the x's q. Minus q squared plus 5q plus 3. Now let's double check we can't simplify anything. Okay, we've got a q squared, a q, and a constant. We cannot simplify anything. That is essentially what we do. So it's not very helpful, but it's just showing you that you can interchange any variable you want, right? You can plug in anything. The same process works for variables. Let's talk about one other instance in example 6.2. And then I'm going to let you guys try a few on your own. So g of x is equal to 2x plus 3. Find and simplify g of a plus 1. Now this is a little bit different. This isn't just a number. This isn't just a variable. It's actually both. But the rule still applies. When you have something in the parentheses, they're saying take that and plug it in. Plug it in no matter what it is, whether it's a number, a variable, a picture of, Jesus, whatever you want to plug in, right? Plug it in for you, okay? So let's go ahead and do that. Instead of g of x, we'll write g of a plus 1. And then every time I see an x, there's only one instance of x here, a 2x. I'm going to keep that 2. I'm going to keep that constant of 3, right? I'm going to keep that constant of 3. But instead, I'm going to plug in an a plus 1. So I plugged in an a plus 1 instead of x. There it is. That's what it was. And then it says to simplify because we actually can here. Let's simplify a little bit. We can distribute that guy in there. So we got 2a plus 2. And we still have that plus 3 on the end. Or we get 2a plus 5. And that's our new function. So g of a plus 1 is equal to 2a plus 5. Alright, so it's a fun little way to rearrange stuff as well. If you need to do that, sometimes they use that with photo coding. So if you're coding like Photoshop, that kind of stuff, if you need to input stuff, it'll take the pixels and it'll do that kind of thing. So yeah, it's very, very computer tech savvy. Alright, cool. go ahead and try out this next one, just A, okay? Find each function, for each function, find f of 3. I want you to find f of 3 just for A. We'll talk about the other two in a sec, but go ahead, pause the video, and try this one out yourself. Alrighty, so I hope you tried this one out yourself. Remember, if you didn't, that's the worst thing you can do to yourself, because you probably think, this is so easy, I totally get it, and then you totally mess it up on the test, and I'm not going to cry for you if that happens. So make sure that you are trying out every problem. It doesn't matter if you get it right. It really doesn't. Right now, it really doesn't matter. You are testing out what you know and what you don't know. It matters whether you get it right or wrong on the test, and if that's the first time you try, that's the first time you will fail. So just a little heads up warning. Alright, let's try it out. So f of x is equal to 3x minus 7, a function defined with the independent variable of x, right? That's what we're saying here. We have this function, our independent variable is x. Let's figure out f of 3, which means we can plug it in. 3 times 3 minus 7 instead of 3 times x minus 7 is 9 minus 7, or 2. Perfect, that's what you should have gotten. So f of 3 is equal to 2. If you have any questions at all, please make sure, I hope you had already gone over them. Otherwise, make sure you go over them now. Let's take a look at this function, though. It is a function, right? We can see that each x is independent, right? There's no double x's that go to two different y's. How would I find f of 3 here? Discuss. Alright, that's right. F of 3 would be in this coordinate pair right here. Remember that x is equal to 3. What we're saying is to find f of 3, we're saying what is y when x is 3. Just like we were at the very beginning of this section, right? We looked at those ordered pairs and we said when x is 3, y is such and such. When x is negative 2, y is such and such, right? And we would have a value for it. Y is 0, y is 5, whatever it is. And then we would look at if we had any doubles. We're doing the same thing here. It's asking the same question. What is y when x is 3? What is f when x is 3? And we look at this ordered pair and we say that when x is 3, in other words, f of 3, then y is 1. Or in other words, f of 3 is 1. Cool. Alright, the last one, the graph. Let's take a look at that. We have this function here. We don't have an equation for it. Maybe we do, maybe we don't. We can figure it out. But there's much easier ways. So how would we figure out f of 3? Well, it's the same thing as if we had an ordered pair, right? It's the same question. What is y when x is equal to 3? That is the question. That is the question, right? So let's go take a look at it. Where is x equal to 3? Well, here's 1, 2, positive 3, right? And if I look on the line, see, this would be the point 3 comma something. What would be 3 comma something? If we rounded to the nearest whole number, we would say it would be 2, right? So if we were to plot a bunch of these points, right, if we actually found the ordered pairs, we would say that the only one that says 3 comma something would be 3 comma 2, and so when f is 3, or when x is 3, pardon me, f is 2. You'd basically just read the graph. Read the graph. Right? Remember what that question is. As soon as you remember what it's really asking you, then it's much easier to find the answer, right? When x is 3, what is y? That is the question every time you see f of 3, right? If you're given an equation, go solve for it. If you're given a bunch of ordered pairs, go find the one that starts with 3. If you're given a graph, go find the point that starts with 3, right? That's what you're looking for. Alrighty. Let's go ahead, let's do a few more. So we're going to rewrite this, so 6.4, we're going to basically rewrite it in function notation, and then we're going to do this evaluating function stuff. So 6.4a, very similar to what we've been doing before. How would we change this to f of x? How would we change this to a function? First off, is it a function? What do you think? Does it have a domain and range that would satisfy a function? Yes, it would, right? Because you can square anything you want to. So you can square any number, you'll get a unique value. No, you can square an x, you can put any unique x you want in there, right? You're not going to get the same x 2 times. You might get the same y, right? Negative 2 and 2 will both give you 5 in this case, but that's okay. There would only be one answer for every x. One answer for every x. So it's definitely a function. So yes, a function. And therefore, we can replace the y variable with the f of x notation. So we want to place the dependent variable with f of x. So instead of y, f of x equals x squared plus 1. And you may be thinking, wow, that's so simple. But if you don't check to make sure it's actually a function first, then your entire problem goes down the drain, right? You still have to check whether it's a function. Once you've made that statement, then yes, you can change any willy-nilly, and I agree, it's totally easy, right? As long as y is by itself. Alrighty, now we need to evaluate f of 2, negative 2, pardon me, and f of a. So let's go ahead and evaluate f of negative 2. Let's do that over here. Again, what does that mean? What is f of negative 2? What question is it asking? It's asking, what is f, or what is y, when x is negative 2? So let's go ahead and plug in that negative 2. Notice this time, pause right here and notice this time that I put in a negative 2 within the parentheses, right? In that last problem where we plugged in, the negative was on the outside. Notice that here, the negative was a part of the function. It was part of the function, right? It was not the number I was plugging in. Here, the number I am plugging in is a negative 2, and so the negative part is a part of that x, so it is within the parentheses. If you need extra explanation on that, please pause now and go over a few of those problems, because that is one of the biggest things I see when I'm grading these tests. People put the negative on the outside and they make a mistake, or they put it on the inside and they make a mistake. So discuss the differences between the two if you need to. Alright, let's simplify this a little bit. Negative 2 squared is negative 2 times negative 2, or positive 4. And so f of negative 2 is equal to 5. So f of negative 2 is equal to 5. Awesome. And then, of course, we'll just practice that little variable switch. F of a is asking the same question as f of negative 2. What is y when x is a? Well, when x is a, nothing really changes, right? It's just a different variable. You can put in the poop emoji for all I care, right? It's just a squared plus 1 instead of x squared plus 1. Just simply a variable change. Alrighty. Let's do the same thing with b, but if you have any questions, please make sure you ask them now. B requires just a little bit more of a situation, right? We've got a standard form equation here instead of a nice, easy slope-intercept form equation. So we have to do some rearranging. It is not okay to put f of x within an equation, okay? So you can't have 4 times f of x. Technically, there's nothing legally wrong with it. It's just really horrible syntax, and nobody ever wants to see that. So we probably would have asked you to, if you did that, we would have asked you to rearrange it anyways. The computer would. So instead, why don't we just start by rearranging it, and then we can really tell whether it is a function or not, right? Because we're not just going to throw in that f of x willy-nilly. Let's go ahead and rearrange it. So subtract x to both sides. Get negative 4y equals negative x plus 5. And then divide by negative 4, you get y equals positive 1/4 x plus 5/4. Awesome. And even though it's fractions, it is still a function, right? Because it is linear, I can still plug in any number I want to for that x, and I can still get out any number y. There is nothing there. Since the x is not in the denominator, I don't have to worry about getting a 0 there. There's nothing possible that's ever going to make that 4, those 4's equal to 0. Right? There's nothing being multiplied to them. If it was x minus 4, then I might have an issue, right? If the x was actually in the denominator, but it's not in the denominator. So this is just a linear equation. It's just an infinite domain and an infinite range, and therefore it is a function. It's a function. So we can say yes, it's a function. Because we say yes, now we can make that switch. Remember, it's a very easy switch, but you must be able to justify it. If you just throw in an f of x willy-nilly, then I'm going to laugh at you. It's going to be funny. Okay, so now we have f of x. Let's start with f of negative 2. Let's do f of negative 2. I'm going to draw just a little kind of notes squiggle there. F of negative 2, and what does that question say? It says what is x, or what is f when x is negative 2? So let's go ahead and plug in that negative 2. 1/4 times negative 2 plus 5/4. All right. Remember, when you're multiplying fractions, you just multiply the numerator to whatever you're multiplying it by. If you happen to have multiply fraction by a fraction, you'd multiply numerators and then denominators. So this ends up being negative 2/4 plus 5/4. I could reduce negative 2/4, but I already have it in LCD mode, so why don't I just leave it as such and end up with 3/4. So when x is negative 2, y, or f of x, is 3/4. And last but not least, we'll do the a part. If I change f to a, if I change x to a, it really doesn't change much except for the fact that I write an a instead of an x. Cool, done. Again, that last part is just to remind you that you can switch any variable throughout anything. Now remember, if you're doing both, you probably will have to simplify. If you have stuff like a plus 1, you're going to have to simplify it out. But here, if it's just another variable, it's just a variable switch. Alrighty. We're going to talk about one more concept today. It's called a constant function, but if you have any questions at all, please pause now. Make sure you discuss them before we move on. Alrighty, the last concept we're going to talk about is a constant function. Now before we do that, this is sort of a generic form for a linear function, right? Our linear function matches our linear equations, our y equals mx plus b. Why they decided to go with ax plus b this time is really beyond me, but that's the one in your book, so I didn't want to confuse you. Really, it's just mx plus b. As we've seen in the last 4 examples, you can switch any variable you want, right? So m and a, same thing. I will always use the second one because I like consistency. I think m is slope every single time. So instead of using this, I will probably use this just to keep things consistent, but really it's whatever variable you want. Sometimes though, m is not there. Sometimes you have 0m, right? And we've seen these equations before. You've seen these as y equals b, right? And what kind of situation do you get when you have y equals b? Or in other words, if b was a number, y equals 2. Who remembers? Pause and talk about it. It's going to be on the test soon. Alright, when you have y equals 2, that's a horizontal line, right? A nice, pretty horizontal line with 0 slope, and it goes across at 2, right? So y equals b would be the same thing. And therefore, since it passes a vertical line test, right, it is a function. It's a function. Passes a vertical line test. Woohoo! Yay! Well, at least one of them does. So passes the vertical line test because it's a horizontal line, right? And therefore we can call it a function. F of x equals b. What about a vertical line? What about x equals 2? Would that pass the vertical line test? Where if I drew a vertical line down this vertical line, do you think it would hit more than once? Yeah, in fact it would hit an infinite number of times, right? If I drew a vertical line going down this vertical line, it's going to hit there and there and there and there and there, and so it definitely fails. Not a function, right? It doesn't even have a slope. It's D&E for slope, right? It doesn't have a slope. It's not a function. These ones really aren't that cool. We use them to pass actually test with a vertical line, but these are not functions. So we would never have f of x equals like x. It's not even possible to write that, right? That doesn't even make sense. There's no y to change to f of x, so it didn't even make sense, right? So vertical lines are not functions. Horizontal lines definitely are, though. They are called constant functions, which makes sense, right? Y is equal to a constant function. Cool. Just know that they're out there. We'll graph one in just a sec, but if you have any questions, let me know. Last thing, let's graph each function and state its domain and range. Let's graph this guy. So you'd think graphing a function, oh no, it's going to be a whole different process that I have to memorize. No, it's exactly the same thing as graphing an equation. So let's just graph it. I've got 1/4 x minus 5/4. 5/4 is my y-intercept. I'm graphing this exactly as if it said y equals, I'm not going to write it there because clearly I don't have enough room. I'm graphing this exactly as if it said y equals 1/4 x x minus 5/4. Exactly as if it said that, right? Because we just talked about that. We just said that this is a function. And so we will say that this is a function, right? Same thing. So I'm going to graph it like an equation. Here's my y-intercept, 0, comma, negative 5/4. So that means I'm going to go down a whole 4/4 and another fourth. So right about there. And then I have a slope of 1/4, which means from my starting point, I'm going to go up 1 and over 4. I'm not going to go back a fourth. I'm going to go up 1 and over 4. So up 1 gets me back to about there, a little bit. And then out 4 to right about there. I'm not going back all the way to 0, right, because this goes over a fourth, or it goes over. And then I can graph the function with a nice straight, oops, do a straight line through both dots. And we have that. It's not an inequality, so I don't need to shade. And I've graphed my function. Beautiful. Very nice. Alright, the last one, graphing a constant function of f of x equals to 4, right? It's the same thing as graphing a what? Horizontal line equal to 4, y equal to 4, right? Remember, those are the same things. Those are always interchangeable. Always interchangeable. So if you remember how to graph y equals to 4, which means you go up and draw a horizontal line through 4, then you know how to graph f of x equals to 4. They are the same thing. Alrighty. Just a little review of what we talked about today, since we talked about a whole bunch today in this 3.5. We talked about independent versus dependent variables, right, and how they relate to x and y. We talked about how those two relate to each other and whether or not they give us a function, right? Only one independent to one dependent, right? And then we went through a whole bunch of examples of what looks like a function and what is not a function from some specific stuff. And then what we saw on a graph. We talked about domain and range, right? Whether it's a specific domain and whether it's a specific range or whether it's more of an interval or not an interval. And then we talked about domain and ranges with equations, right? And those can get a little tricky there. So make sure you review those in your homework tonight. Talked about function notation and how that works and how it's pronounced f of x, not f times x. And what that means when you plug them in, and variables versus numbers versus expressions. And then we talked about finding f of x on 3 different things, like an equation, a ordered pair set, and a graph. And then finally we talked about graphing function notations. Very nice. If you have any questions at all, please make sure you get them answered as our test is coming up. This does conclude Unit 3. We have a lot we've been talking about, so please make sure you use this time. We will have a review day, and then we will have our test relatively soon.